Hello and welcome. In this video, I'm going to be talking about the relationship between the computer programs that we write and two very common yet not really well understood mechanisms for interacting with users on the command line. That's right, today we're going to be talking about standard in and standard out. I'm going to start things off with a brief overview of what standard in and standard out actually are, how they're laid out in memory, and then I'm going to jump straight over into the code so I can show you how you can actually use them to help troubleshoot problems on the command line regardless of what programming language you're actually using. It's going to be great. Let's get started. Okay, so I think I'm just going to start us off with a quick overview of what are standard in and standard out. So I have some high-level definitions written here on the screen. Standard in, as you can see, is really just standard input. It is often written as stdin. And standard out is just standard output, often written as stdout. These are definitions, you can read them, I'm not going to. The big takeaway that I want you to have from this particular slide, though, is the use of the word operating system, okay? So this is the first misconception I want to make sure that I get addressed right away, is the idea that input and output, especially when it relates to command line interface, are not programming language specific. It's not as if C++ has a different way to interact with the CLI than C# does or than Java does or whatever. They all are at the mercy of how the operating system implemented their standard input or standard output mechanism. All right, so these are operating system specific mechanisms, and that is important to understand because it also allows you to understand that there's a standard way that they do it. And that standard is what we use as programmers to allow us to string programs together. And that's why you can use the word source and target here, because the source doesn't necessarily have to be one specific thing. The source can really just be anything that has information that comes into this standard input section. And then when you have output leave your program, it is going to go to standard output, right? Which is a standard way. And that output could be actually sent to many places, not always just to the CLI terminal for like actually being seen by a person, but it could actually be sent to another program. So those two understandings that these are standard operating system delivered mechanisms is a key first step in our journey. Okay, so the next thing I wanted to briefly talk about was random access memory, or RAM, and more specifically, the relationship between a computer program and RAM. Now, my hope is that this is something that most folks who are watching the video have some level of familiarity with. If not, I'm going to just do a quick overview of it. But this is really a paramount piece of information for anybody who is a computer programmer or an aspiring computer programmer. And this exact same understanding will be very useful for us when we continue talking about standard in and standard out. So, briefly, when you have a computer program, it is going to interact with RAM. RAM is the place where all of the memory that is actively being used by your program lives. So RAM is actually split up into two sections. I have three here, but that's just for pictorially, visually, making this a little easier to understand. But the two that I have highlighted here right now, the address and the value, that is what RAM is completely made up of. So RAM is really made up of these two pieces of information. One is the address, and what addresses are literally just numbers. They are numbers, they are contiguously stored. So RAM in your computer, which is a physical thing that you put into your computer that's like plugged into the motherboard of your computer, it has a physical amount of space that it can hold. So these RAM addresses, like I said, are just numbers. They're actually quite large numbers. For the purposes of this picture, I went ahead and just used very small numbers, and I made the address go up by a byte every time. So we started out, I skipped 0 because that's technically a reserved spot of RAM, but we would start at maybe 256, and then another byte from there would have us go up to 512, another byte from there, 768, so on and so forth. And this actually would just go on and on and on and on. But those are the addresses. They are fixed values, and that is just where they live physically on the RAM stick. Now, let's say you're in a program and you have a variable. So let's say you have an integer, right? And you name that integer the variable x. and you assign it a value, let's say 42, okay? In this scenario, I guess it'd be a compiled language, I want you to allocate an integer's worth of space in RAM, and then I want you to assign 42 as the value at that location in RAM. Okay, that's really what this, when you declare variables, that's what you're doing. You're telling the operating system, I need space in RAM, and this is how much space I need. And going forward, this is how I'm going to refer to that very specific spot in RAM. Okay, because you don't want to have to remember space 512. And like I said, these numbers are actually much bigger. So you don't have to remember space like 5372967, like some huge number. You want a nice variable that you can name whatever you want. Okay, and that's why we have variables. So in this case, if I was going to try to represent this this declaration in my little RAM diagram, your operating system might say, okay, let's just pretend for the moment that the operating system was going to have us start here at 256, like that was where we got allocated space in the RAM stick. And it might go, okay, an integer, let's say an integer is only 1 byte. That's actually not true, but let's say it's only 1 byte. In which case, that would mean that this column that I had here would represent the entire amount of space that could be represented by x. So in my program, the variable that I'm using is x, but x is now being tied to address space 256. And the value that we're going to associate at address 256 is the number 42, right? If later on in my program I, let's say, had a Boolean, and I named it Boolean y, and I set it equal to true, okay? Well, in that case, the operating system is going to continue to look at spots in RAM and go, okay, well, this address space 256 has already been taken up by, this value of 42. So I have to put this y in a different place. So it might decide, well, the very next spot is looking pretty good, and I'm going to put true here now, right? In reality, it would actually just store a 1 because that's what Booleans are, is 1 or 0. But that's where that information would get stored. So ultimately, what I'm trying to showcase here is that there is a relationship between the variables in your program and where that information is stored in RAM. And having a good understanding of that relationship is quite important, especially for what we're about to talk about next. Okay, so now that we've sort of revisited what RAM is, we're going to take it another step further and talk about how RAM is sort of set up for a specific process. And when I say process, I basically mean computer program. Those two words often get interchangeably used by folks who are talking about computer stuff. So this is sort of a quick little diagram of how RAM is sort of divvied up for a process. So when you launch a program, you basically tell the operating system, hey, start running this program. One of the first things that the operating system is going to do is decide what space it's going to give in RAM to this process, to this program, right? So it basically just hands that process a whole big chunk of RAM and says, this is yours to play with. And when it does that, RAM is actually divvied up into a bunch of different segments. Now, I'm not going to go into every single one of them right now because that's not really the focus of this video, but I do want to point out that part of what you get when it divvies up the RAM is standard in and standard out. So these are actually parts of the RAM that your process is given when you launch the program, right? So this is actually like built into your program. So when you are running your program, you have a little section of RAM that is specifically designated as standard in, and another little section of RAM that is designated as standard out. Okay. Now, the point of this diagram is that I want to showcase that what standard in and standard out really are buffers. They are basically just little chunks of space in RAM that you get to use to write information to or read information from. They are specifically set up by the operating system for the express purpose of reading information in from CLI and writing information back out to CLI. So when we start talking more and more about standard in and standard out, when I start jumping into the code, I think the easy and the best way to think about this is to think about them as a buffer. Standard in is just an input buffer, and standard out is just an output buffer. And that they are taking up space in RAM alongside all the other things that are in RAM, including your variables and whatnot, right? So all of the stuff that you created in your variables and your functions and all that other stuff, that's all taking up space in RAM as well. But those are things that you, as the programmer, have control over. You can decide what those variables are and what they're called and what they do. Whereas standard in, standard out, these are just things that are going to get loaded into the RAM section for your process, and they are where all other programs that are going to read information out of your standard out, they're going to go to that particular spot in RAM that your operating system set aside for your specific program. Okay, so these are just buffers. That's really all they are. So to piggyback on how standard in and standard out are just buffers that are part of what you're allocated when your program is launched, I have another visual here that I'm hoping will really cement this in. And I've actually written a little bit of code here to hopefully show the connection between that buffer and the various programming languages that utilize this buffer. So in this case, my buffer is actually for the standard in. So you can kind of think of standard in as these blocks are meant to represent this little part here that I had in yellow. Okay? All right, so that's what this little block right here represents. And notice how when you first start your program, there's nothing in this block. Its input is completely empty because nothing is being sent in. Or at least in our example, it is actually possible for us to push information into standard input. I'll show you how to do that in a little bit. Okay, but for now, let's assume that it's completely empty. All of the different programming languages that you've ever used all are basically interacting with this standard input buffer. So I have some examples down here of different programming languages and how their syntax is designed to read information from standard input. And the important thing or the part I'm really trying to emphasize here is that even though these look very different, all of the actual syntax for these languages is quite different on how it's collecting that input. In the end, every single one of these is just pulling information out of standard input buffer that is being supplied by the operating system. So if I go into the standard input and let's say I am collecting it from the CLI terminal through like just typing on the keyboard. Let's say I typed the word hello, right? And then I hit enter. So if I hit enter, that would be a new line, or like a \n, you can think of it as like a new line character. So once it sees that, almost all standard input buffers are implemented such that when they see a new line, that's their signal to go ahead and just send the information from the buffer into your program, right? So when they see that new line get tapped in when you type it on a keyboard, what that tells the program is take anything that's in this space and start mapping it into anywhere in your program's variables that you've set aside for that data, right? So it starts here and then it ends up wherever you wanted it. Okay, so in this case, if I typed hello and hit enter, in C, the way I would capture that, and I'm assuming here that you've created a variable in your program named myInput. Okay, so it's a string named myInput. So in that case, in C, how would you use it? Well, you could use this fgets function, and you're basically saying, okay, take the size of my input, because usually in C you would have to say how big this is. So like let's say it was like you set aside like maybe 100 bytes or 100 characters for it. You say okay, map anything from standard in that is up to this size and put it into this variable that I have there. So all of that, it's a kind of elaborate way to do it in C, is ultimately just saying read the information out of standard input and bring it in and put it here. Put it into this variable. So that's how standard input works in that situation. For C++, it's a little bit nicer. In C++, is a more object-oriented language, so they have an object called cin, which actually represents standard input. And so this object is actually mapped to standard input. So when you reference it, what you're really referencing is this input buffer, and then you can use the extraction operator, which is what this is right here. And the extraction operator will extract information out of the buffer, right? And it'll push it into whatever variable you have it mapped into. So it's a lot nicer in that case. If you're using Go, that's the other language I'm going to put in here, Golang. Their way of reading information, they actually have a few different ways, but the way I have showing here is scanline. So FMT is one of their packages. You could use scanline, and then you actually have to just tell it the name of the variable, and then you use the ampersand to represent the address space that you're actually trying to read it into. And that's actually kind of nice in Go because it's kind of letting you know this is to a specific address location. This is a very specific place. It's a specific number that I need this to go to, but I'm going to call it in my Go program is my input. Okay. So that's how that's set up. And then of course Python's a real popular language nowadays. Theirs is pretty interesting. They have an input function, right? And so you can actually put some prompting in here if you want. In this case I've not. I'm just saying literally just call it input. When it sees this function, it reads all the information out of standard input up until a new line, and it'll just map that data directly into a variable. So even though all of these look very different, depending on what language you're using, they seems like they're very different looking, but in the end, they are all doing exactly the same thing. They are reading information out of this buffer and using that to push the information into a local variable. All right, we just did standard input, so of course now the last thing we're going to show is standard output. So output is pretty much exactly the same thing. Just like how standard input is really, you can think of it as a buffer, standard output is indeed just another buffer. Instead of being read information from it and going into your program, it's really the other way around. So instead, in this situation, you would be taking information that lives here in the little green section of your program, and you're wanting to send that somewhere outside of your program. Well, lucky for us, when we spawned the process, it set up this little chunk, the part that I put in purple here. It said it set aside this space in RAM as like anything you put in here, I will send it out of the program. So what you really are doing when you send something to standard output is you're basically kind of like copying that information out of this section of your program and putting it into this part of RAM that's attached to your program. And that's just because that's the spot that the operating system is looking for when it wants to actually take your information and go somewhere with it. Okay. So in this particular case, I'm showing again all of the different ways that you can use standard output with various languages. So if you were writing a program in C, the most typical way you would do that is using a printf function. In this case, you'd be writing the word hello, and then there's actually a new line character at the end of that. So again, if we were doing this, it would be something like HELLO, and then of course that new line character is actually part of the thing that goes in there. Right? And that's another thing to understand is that when you write information to the output buffer, anything that you put in there that is a character is put into the buffer. That includes new line characters. It includes spaces. It includes pretty much anything that is a recognized character from that language, which for most languages is going to be something in Unicode or ASCII, or which is just a small subset of Unicode. It's all going there, right? So this is how C would do it. This is how you would do it in C++. Again, it's using an object, cout, and this time it's using the insertion operator. So it's basically taking this string and the arrows even showing you, it's pointing it into what cout represents, which is the output buffer, standard out. If you're using Go, you're going to use that FMT package again. You're going to say FMT print, right? That's one of the functions they have associated with it. You can actually just print the information that way. And then, of course, good old Python has just plain old print right there. Push that information out. All of these, for the 4 different languages I have represented here, are doing exactly the same thing. They look different, but in the end, they are all going to standard output. That is just where they all go, because that's the place that the operating system is looking when it wants to actually have information leave your program. Okay, so now that we've sort of gotten out of all of the sort of high-level description of what's going on and how input comes in through standard input and how output leaves through standard output, and hopefully got a better appreciation for how those two mechanisms are sort of implemented in a computer system, let's write some code. So what I've actually done here is I've actually written 4 different programs using 4 completely different languages, and each one of these programs are basically doing exactly the same thing. So here's a C program, and they're all going to do the same thing, so I'm just going to show you really quick. And it's going to print the words hello and welcome, or welcome to the fake program, a couple of new lines after that. Then it's going to collect, ask them to enter their favorite color. They're going to enter their favorite color. Then in this case, it's just going to have to do some finagling with C to make sure it doesn't capture that new line character. And actually, this is a good point in having it here, is that like, even though they all are going to use standard in, how each language parses standard in is actually that is unique to the language. Which is why some languages it seems like it's more of a hassle than others, is because that's just how the language was initially designed. So case in point here, With C, when you use fgets, which is like a really common way to read information from a particular buffer like standard in, well, you have to tell it how big you're going to read in from, like how many characters am I reading up to, right? So that's why I had to tell it, well, I'm going to read up to the size of fave color here, which is a variable. It's 100 characters, so basically a string that can hold 100 things, 100 characters in it. Well, when you use fgets, it actually will read everything up to, in fact, I'll come back over here. It'll read everything, including the new line that they typed in. So this piece right here, this new line at the very end, that also is going to get read into the program, right? It's going to get read into the variable that I'm capturing. So to make it so that doesn't actually stay in that variable, I wrote a little bit of extra code here to go look and see like, well, if the very last character that you read in is a new line character, then let's just ignore that and just replace it with the null terminator, which is how the C programming language knows it's the end of the string. And then I go ahead and just print out, you entered whatever they entered, that's a great color, okay? So here, let's just go ahead and run this really quick. I'm going to go over to my terminal. We're going to close that guy down. And let's just do it. So in C, I'm going to use GCC to do this. And I'm going to tell it to go ahead and compile the example.c program. And when it does this, it ran it just fine. It produced an executable, which is right here. So now if I run the executable, welcome to the fake program, enter your favorite color. So when the program first started, there was nothing in that input buffer. Nothing was being passed into this program. So it's sitting here now waiting for me to give it some data because it's waiting for that input buffer to get filled with something from standard in and then get passed into my actual program. So in this case, I'm going to type in, I don't know, blue, right? And then once I hit enter, enter is the way that the program knows, oh, okay, you are now ready for me to send that information from standard in and send it into your actual program for it to process. And indeed, once it did that, then it was able to complete the rest of the program. You entered this, what's your favorite color? Now just to showcase what would happen if I actually got rid of this, and here's it's just kind of showcasing why I had to have that piece in there with C, right? Let's see what happens when I run it now without that. So I'm going to recompile it now, and I'll rerun it. Now I'll say blue again, and see what happened here. You entered blue, but look, then on a completely separate line, we had the comma, and then that's a great color. Why did it do that? Well, the reason is because of how fgets works. This particular implementation, this language chose to parse that input buffer in a very specific way, read the information out of it, and part of the way it did it was it kept that new line character that got passed into the input buffer when I pushed enter at the end of typing in blue. So this is just something to understand, like that's why this is happening. If you don't really understand what standard in is doing, or in particular what fgets is doing, this might just seem like weird behavior to you. It might also seem weird that I even had this code in here to begin with. You'd be like, well, why is this even necessary? What is this doing? Right? Another good rationale for having good comments, I suppose. But having a good understanding of how standard in and the language you're using to parse standard in is paramount for you to actually fix these sorts of problems. All right, let's go ahead and move on. That was the C program I had as an example. All right, I also have a C++ program. Okay, so here I am in C++. Does exactly the same thing, except that now I'm using the good old cout object, and I'm using getLine to do some stuff. So let's just do that. I'll use G++, and we'll do example.cpp. Do that. Produced an executable. Run it. Favorite program. This time it'll be yellow. And you entered yellow. That's a great color. Now notice in this one, I didn't have to do anything like that with the standard in. I didn't have to like remove that new line character because that's something that the getLine does for me. It actually went ahead and just took that out. Also, it could also be, I actually don't remember if it's getLine or it might be cout. Cout object might very well, when I pass it into the insertion operator, I think it actually strips out any leading new line characters, which is why we didn't have to deal with that. So again, sort of a simpler program here, right, compared to the C program, does exactly the same thing, but both of them are using standard in. Both of them are doing that. All right, let's move on to Go. Okay, here's a program in the Go programming language. Right, again, a lot of similarities. Welcome to the fake program. Enter your thing. This time I'm using scanline for do it. I'm using print and print line to do all the output for standard output. Okay, so let's do this. I'll just do go build, and then we'll do example go. And I love that Go always takes a little longer. All right, there it is. It produced an executable. In this case, it just called it example.exe. So we'll do example.exe. We'll run it. Welcome to the fake program. A favorite color this time will be red. You entered red. That's a great color. So look at that. It's still working. All these languages, they're all doing exactly the same thing. And of course, Python, probably the most simplistic of all of the languages I've chosen. This is actually an interpreted language as opposed to the others are all compiled languages, or they're implemented with a compiler. So in this case, I'm just going to run Python, and then I'm going to tell it to use example.py. And welcome to the fake program. What will we end this with? I guess we'll end it with green. And you enter green. That's a great color. Okay, so hopefully I've demonstrated now that all of these programs do exactly the same thing. There's nothing overly special about any of them. They all have different syntax, right? But in the end, they're all using the same mechanism under the hood to do this. Now, the problem with when you write programs, and this is where we're going to move into some tips here. When you're writing programs that take input from the CLI, the most common way for people to test those sorts of programs is to do exactly what I just did. They come into the program, they run their program, and then they, on the keyboard start typing stuff. So they'll write in, I don't know, whatever. Now, let's say teal is my favorite color, right? And they hit enter, and that's how they do it. And when you do it this way, there is an easy to confuse sort of situation that happens. And that is you look at the output and it kind of just looks like it's all output, right? It's not easy to look at the part I have highlighted here in blue and see what and know intrinsically, unless you were the one who just typed it seconds ago, what is this is output and which of this is input. Because the reality is that this stuff right here, that was all output. This is not output. This is input. This was tied to a completely different buffer. It has nothing to do with output. This new line, that's output, so is this, right? And that's not super obvious, and this can sometimes get folks in trouble when they are trying to write, computer programs and figure out why their output isn't happening the way it should, or their input isn't happening the way it should. Case in point, let's go over to, I'm going to do an example, and I'm going to use C++ in this case because it's a real easy one for me to use this example for. So in this case, I'm going to actually use a different way to collect the input. So I'm going to say, instead of getLine, I'm going to use cin, which is what I used earlier in my example. And I'm going to say fave color. Okay. Now there's a difference here between what getLine does and what cin, and this is also showcasing that the mechanism that the language uses for parsing standard input really makes a big difference for how the input is going to be read into your program. Because if you don't really understand that in the end what's happening is it's actually just parsing this buffer, like all of the data is sitting there. Oh boy. All of the data is sitting there. All of it's there. It's just that depending on your language, how it chose to parse this buffer, it's going to potentially pull that information into your program maybe very differently. Okay, and that's basically what's going to happen here. How getLine works is very different than how cin and the extraction operator works. So in this case, I'm going to do this, and now watch what happens here. I'm going to say, actually here, you know what? Let's just do this really quick. Go back to the way it was, just to showcase what this looks like. G++ example.cpp. Okay, I'm going to run the program. What's your favorite color? Now I'm going to say it's bright red. Okay, you entered bright red. That's a great color. Isn't that great? So it did everything the way I thought. Now watch what happens when I change it over to the cin with the extraction operator. And now I'm going to say A, and I'm going to say bright red again. And this time, you entered bright. Okay, it didn't capture the red. That is a product of how the extraction operator works. The extraction operator, if you come back over here, it actually, when it sees a space, it stops parsing the information out of the input buffer. That's just how it's designed to work. However, when it does that, it actually leaves the information still in there. So if I were to undo this right here and just make it more keeping with what I just typed, right? So if I were to now type in, let's say B-R-I, I'm just going to do it like that. Let's say I had a space here, and then I had R-E-D, and then my new line. Okay, let's say that's what's at the input buffer. When you use the CN object in C++, it will read right up till it gets to here, and then it stops. And this is the only part that's actually going to get read into your variable, which is exactly what you just saw happen here. Now, the funny thing is that if you don't really understand what's happening, if you don't understand that this buffer still has all of this information sitting in it, then it can be very confusing when the very next thing I'm going to do is I'm going to come over here and I'm going to say cn fave color again, and I'm going to say cout the remainder, right? And we'll just do fave color. And what's going to happen now is, let's go ahead and run it. Go to the program, bright red. You entered bright. That's a great color. So again, it messed up. But then it said the remainder red. But notice what happened. It didn't stop. The program didn't stop when it got to this CN fave color. Why? Because what is this part of the code doing? It's actually trying to read the information from the input buffer and map it into this variable. Well, when it got to this part of the program, it had already read this part, so this part was still just hanging out in the buffer. This part was still just hanging out in the buffer. So it literally just read that part of the buffer in and moved on. It said, cool, here's everything that I needed. It's all right there. And it moved on, and then it just printed out whatever it read from the remainder of the buffer, which in this case was red. Now again, if you don't really understand how the input buffer is being parsed or how it even works or the fact that there even is an input buffer, this would seem like potentially very confusing behavior. And different languages will do this somewhat differently. And so having that good understanding can really help. The last thing I'm going to do, just to kind of really showcase this, and actually I'm hoping that this will be a nice tip for anybody who's ever trying to understand how a program that they wrote, or maybe even a program that they're just maintaining, is pushing information to or from the input buffer or the output buffer, is I'm going to actually use some scripts that I wrote to help navigate this. So first I'm going to do is I'm going to turn this back into what it's supposed to be. Okay, there's that. All right, and I'm going to show you the script that I wrote. Okay, so this is a PowerShell script. The only thing that it does is it basically just automates the process. Well, actually, this is the PowerShell script. It just automates the process of running these programs. So basically, I can pass to this script the language that I want it to compile, right? So I either am going to pass it a C, C++, Go, or Pi. And then, depending on which one I give it, it's going to compile it, compile the code that's associated with that particular language by doing one of these things up here. So you see how it's just doing the same thing that I was doing, C++ or GCC. I'm actually using C++11 in here, but I guess it doesn't really matter. Or I'm using Go, right? So it's just doing that, and then at the end, it's just going to run the program immediately. Okay. So all I did here was I just automated it. Now, the real trick is this. I am going to pipe in to the program the input. So I'm not going to type the input that's actually going to go into the program. So earlier when I talked about what the input buffer does, right, I guess we can take a little journey back here. When I said what the input buffer does is that it is something that standardizes from a source, okay? And again, the source doesn't necessarily have to be something that was actually typed in the keyboard. It can just be something that was given to your program that can get passed into the standard input buffer, right? Which is exactly what I'm doing here. I'm creating a little string, and this in PowerShell, this is just a string that holds the word green because that's the only input I'm going to pass in because they all were just asking for a color. And then what am I doing? When it's time for me to run the program, all I'm going to do is take that string and I'm going to use this pipe. And that's a really typical CLI tool to take the input or the output from one thing and send it as the standard input into another thing. And by doing that, here's what we're going to do. I'm going to say automate input.ps1. Let's do C first. So here's the C programming language, example.c, compile, run, and look what it did. Welcome to the fake program. Enter your favorite color. You entered green. But look, no green here, right? Because that was input. And input is not the same thing as output. So when I told it to just run this and just immediately show me the output, that was the only thing that I saw. Is I'm literally only seeing stuff that was sent to the output buffer. The input is not something I had to type in. It got that when I fed it up here. So just to prove that this really is not unique to C or C++ or whatever, I can now do this exact same thing with any of these programs. If I do this with C++ now, and I just pass it to the CPP file. Welcome to the fake program. You entered. Notice how there's nothing in the input buffer still, right? It doesn't matter if I do that with that, or let's try it with Go. 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 Same deal, right? And then, of course, last but not least, Python. So we'll go over here and we'll do py. And this time I'll do example.py. Welcome to the fake program. You entered green. And I'm trying to demystify this notion that there's something special about these programs. Like that the languages themselves have some special thing they're doing. They're all just using the input buffer. They're all just using the output buffer. Now here's a little tip. If you're ever in a situation where you're trying to make sure that you want to know exactly what the output of your program is, but you don't want to have to confuse that with the information from the input buffer, well, hopefully this is showcasing that. But I have noticed that this is a really nice strategy, is not only to just do it this way, but if you really want to see what's getting pushed out to your program, pass it and have it redirect to the output completely, right? And what that means is what I can do is this. I can actually just go down here a little bit further. In the same way that I could pipe information into standard input and have that information then get pushed into my program, I can actually redirect the output of my program. I can basically change where standard output will go. So my program is going to write a bunch of information to standard output. And by default, that's just going to get printed to the terminal. But I can tell it, no, standard output now is going to actually be something else. What if we said it's actually just going to go to a file called output.txt? What if we did that? And then here, I'll do the same thing here. We'll do output.txt, even if it's in Python. Okay? By doing it this way, I am now telling it, take everything that you were going to do it, and then instead of printing it out to just the CLI, push it into this file. Let's do it again here, and we'll just roll through the top here. Here's the C programming. Now look, nothing happened here, but look what showed up, output.txt. And if you go look over here, this is what the output of the program is. But the cool thing here is now when I'm looking at it, I know exactly what the output is. I know every little space that it added in there. I even know that this program ended with a new line because there's a new line underneath it right here. That's not always obvious when you're running it in the CLI, when you're running it down here. Like, depending on what shell you're using, it might add one or not have one. When you write it to a file, it becomes very clear. It also makes it very clear if you have any random spaces in there. So for instance, let's say I changed my program. Here, I'm using the C program right now. Let's just do it. Let's say I had a random space right here, right? Or I had a random space right here, a couple of them, right? Well, if you do it this way and you don't have it printed to a file, right? It's not obvious where those spaces are even there. You can't really see them. They're just not here, right? But if you come back in here and you do this and you actually send everything that was in the standard output buffer to the file, and when you run it, hey, look, there's a bonus space right here. And look, there's a couple bonus spaces right here. Like, you can actually see them. I zoomed in there so you can see it a little better. There's a couple little spaces right there. It becomes clear what your output really is for your program. It also lets you see just your output as opposed to only looking at your input. By running it this way, I actually know exactly what's being passed into my program. I know exactly what it is. It's this, right? And I know exactly what's coming back out, even down to where new lines are, where spaces are, where everything is. And this can be a very handy tool for when you're trying to troubleshoot problems related to input or output from your program, especially when you start trying to map the output from your program into other places and it's not working the right way. This is a good way for you to figure out, oh, this is what I'm passing to that program, and it's not expecting these two extra spaces. That's why it's having a problem. And just to showcase that this will work for any of them, really. It's not something special or unique to this. In fact, here, let's get out of here. Let's go over to, let's go. Why not? And in this case, let's say maybe this time I wanted to put in, here, we didn't want to put in that extra new line at the end. Let's see what happens if I get rid of that. Space. Okay. And we'll do go this time. There's the output.text. And look at that. There is a new line character still getting out at the end. That's kind of weird because I told it not to, but it's still somehow there. Kind of curious why that happened. I think that probably happened because we're using PowerShell. So this is another thing to understand is the shell you're actually using will sometimes dictate what gets pushed to input and output. In this case, there's still a new line here. Now, just to showcase how this would work in a different shell, I'm using PowerShell right now. Let's switch over to Ubuntu. So now I'm running this program. I'm going to run everything in a completely different operating system. So Ubuntu is a different operating system, has nothing to do with Windows. I don't even have PowerShell. Well, I've written a completely different shell script. This time I'm writing it in Bash. Okay, so that's one of the most common shell systems for Linux-based operating systems, but there are others. It doesn't really matter. I'm writing a shell script. This shell script is designed to work exactly the same way. So I'm basically just passing it in the kind of language I'm going to use first, and then it's just going to compile it, and then it's just going to run it at the end. I'm using a little bit of different syntax to do it, but in the end, I'm doing exactly the same thing. I'm taking the input string that I gave it, I'm piping it into the program, and then I'm going to have it send it somewhere else. Now, in this case, I'm going to go ahead and update this and just say, here, we'll do Ubuntu output txt. And I'll copy that, and I'll do it for both this and that. And we'll come in here. And now I can automate the sh. And let's do it for, which one did I do this for? Go. Go and example.go. And do it. Okay, and there's my Ubuntu output. And looky there, no more extra new line at the end. And now, because they're in files, actually your life gets even better, because now let's say I wanted to compare between what it looks like in Windows versus what it looks like in here. Well, I mean, I could just flip back and forth here, but if you're using a neat text editor like VS Code, look what else you can do. You can just grab this one, and hit Control so you can select both of them. Right click, compare the selected, and look, it'll tell me exactly where the difference is. In the Ubuntu one, there's no new line, but in the PowerShell one, there is a new line, even though it's the same code, right? So it's that. What is that telling me? It's telling me that the shell for PowerShell does something different than the shell for Ubuntu. And that would be very unpleasant to try to figure out if you don't really understand how an input buffer or an output buffer works, or even how they might be different depending on what shell you're doing it. It might not even occur to you that it's a shell problem because shells are connected to the operating system. And if you don't know that input and output buffers are connected to the operating system, that's really hard to debug. The last thing I'll show, since this video is going on a little long, is I'm going to show how you can also see these little dots. I know that sometimes people will look at this and be like, that's great, but I don't, how do I see these little dots? Because those spaces are sometimes hard to find in my little output. Real easy to do in VS Code at least. Pretty sure you just go to Edit, and I'm pretty sure you want to say, or maybe it's View. Yeah, say it's View, and I think you want to do Appearance, and then is it, yes, render white space or render control characters. So if you come down here and you check those, then you will actually see a little dot everywhere that a space is being output in a file. Won't work on the CLI part, but it will work here. It'll work in these files. And being able to do file comparisons is extremely handy. It's extremely convenient way for you to do a lot of comparison of outputs. It can be very handy. So anyways, that's pretty much this video. I hope that this was informative. I hope you learned something from seeing how the input buffer and the output buffer work for programs. I also hope that it helps illustrate that they aren't really language specific. You can do anything that I just showed right here with pretty much any language you want. I picked 4 popular ones, but it doesn't really matter. Any language that you can think of will subscribe to needing the output buffer and the input buffer to do certain things. And so when you're trying to do that troubleshooting related to those kinds of buffers, here's a nice way you can do it. Right. Well, thanks again for watching, and happy coding.